So this is another example where we're looking to find a solution to this initial value problem. So this is still going to be done with separation of variables, but we're also going to use the initial value to find a specific constant for that arbitrary constant that will come in through the integration. Now, when you just come across this problem, if you weren't told to use a separation of variables, it might not be your first instinct. The reason for that is there's so much addition over there on the right side that it looks almost like you're not going to be able to write it all as one thing multiplied, right? Because in order to use separation of variables, you need to get the dy multiplying a quantity that involves just y's and numbers, right? And the dt multiplying a quantity that involves just t's. So this is sort of scary looking, right? You might not expect it. A reason why it's going to work, though, is because there's a bit of a pattern here. So if we do some factoring, we might be able to get it to look like what we want. So by doing some finagling of the right side, we can notice that there is a 2t minus 1 staying there, and there's a y with the rest of the term. So I'm going to factor out that y. So 2t minus 1. Notice here that both of those, so here you have a 2t, oops, that was very strange indeed. Sorry about that. We have a 2t minus 1 here, and then a 2t minus 1 here as well. And so in this problem, those are now factors in both of these. So we can actually factor this one better and write this whole thing as one of these groups plus y, factoring out 2t minus 1. There you go. So you can multiply that out the other way to verify it. Now, if you're told to use separation of variables, you are going to have to multiply everything. So this would be a good thing to look for these sorts of properties. All right, great. Now let's go ahead and move everything with y's to the left by dividing. So dy divided by 1 plus y is equal to dt times 2t minus 1. So I'm going to actually just write it like so. Now our next step is to take an integral of both sides. So this will give us, on the left side, we're going to have the natural log of 1 plus y equal to t squared minus t plus some arbitrary constant c. Now we're not quite done yet because we need to get y isolated. So let's do that by getting 1 plus y, raising, so e to the power of the left side, e to the power of the right side. So 1 plus y is equal to e to the power of t squared minus t plus some arbitrary constant. Or you could just say y is equal to that whole e to the t squared minus t plus an arbitrary constant, subtracting off 1. All right, great. Now let's go back and think, well, what was our initial condition? All right, so we had that up above. Let's go ahead and scroll up right there. Great. So when t is 0, y should be equal to 2. So let's plug that in. So if t is 0, so y is equal to e, so 0, 0 to the power of c minus 1. This had better be equal to 2. So to find out what c is, it tells you e to the power of c is equal to 3. So the arbitrary constant, in this case, would need to be the natural log of 3. This then gives you your final solution of y is equal to e to the t squared. Let me write that up a little bit better. E to the t squared minus t plus the natural log of 3 minus 1. And this is a perfectly fine way to write it. You could also, just by using laws of exponents, if you choose, also I've written it as 3 e to the t squared minus t minus 1. If you had chosen beforehand, we could have even, right here when we had the arbitrary constant, a common move you might see is to think, well, if this is, let's just take this over right here and think about this for a second as another way of doing this problem, is you can think, well, e to the arbitrary constant is itself an arbitrary constant. So I could have written this as y equals some value of c. This is a different value, so sometimes you might use a different, like c sub 1, e to the t squared minus t minus 1 is another way of writing that expression.